So we will start with this. We will try to see how these neural networks can be implemented in a general case. I know that the topic is on video, this one. Just to tell how we create a architecture in neural network, I have taken this example because in tomorrow's session, when you start working on deep neural network, so you should be able to understand how we generate an architecture. So I have taken Python, a simple Python with sklearn. I am using here with Keras for implementation. Okay, so this is the older version of TensorFlow. TensorFlow 1 version I have used 1.13 or something. Or in TensorFlow 2.0, the Keras has been integrated with TensorFlow itself. See, for us, these things are just loading the data set and all those things, encoding the labels, means formatting the labels in a standard formats. We call it as a one code encoder, one not encoder, these things. If you want to create any architecture, it is just as simple as this one. Just we need to have something called as model is equal to sequential, because whatever we are using is a sequential model, means one layer after the other. So we have to add layer by a layer, like model.add is a function to add a layer. And dense is for fully connected. As I said, normally all the neural networks will be fully connected. We can add a fully connected, and we have to mention how many number of nodes should be there in that layer. Example, here it says that input dimension is 4. The reason for input dimension is 4 is we have taken the iris data set, and iris data set is a data set. The size of the data set is 150 by 4, means 150 samples, and 4 features are there, neglecting the label column Y. Okay, the 4 features are there, so that's why the input dimension is equal to 4. So as I said, for the input layer, we should have a 4. And we can specify which activation function has to be used, okay, and the number of nodes in the layer, in the hidden layer. So this is an example for the hidden layer. So in the hidden layer, I am telling that, okay, you use 8 nodes. So input is 4. In the hidden layer, we have 4 nodes, 8 nodes. Okay, so 4 nodes will be connected to 8 nodes completely, and each node in the hidden layer uses a ReLU activation function. Okay, and that hidden layer is connected to another hidden layer. So the last layer is the output layer. And we know that iris dataset is a 3-class problem. It has iris setosa, versicolor, and virginica. So it's a 3-class. That's why in the last layer we are having the 3 nodes. Okay, and activation is a softmax. So here you can specify whether you want a softmax or a sigmoid. But normally, as I said, in this softmax is used for the last layer. So like this way, if you want one more layer, you can just add model.add, give the number of layers and what activation function has to be added. Just one line that will create one layer of architecture. Only in case of first layer, we have to give the input dimension. For others, it's direct, so no need to add anything. And to compile the layer, so we use model.compile with which one, like loss. There is a loss function, like as I said, while we are back propagation, we have to mention which loss function, which optimizer. There are multiple things which I have not discussed. Okay, so that we have to specify. If it is a 2-class problem, we use a binary entropy. If it is a multi-class, we will use a categorical class entropy. So optimizers, there are different optimizers. These optimizers are responsible. These optimizers are responsible. Someone might have.
Someone might have.
I am getting the echo of that one. Hello. Yeah, I think.
Yeah, one participant has unmuted. Yeah, one participant has unmuted. Yeah.
Okay. Yes. So we can have different optimizers like Adam,
Okay.
Delta,
Yes. So we can have
SG.
different optimizers like Adam, Delta, SGD.
Ma'am, I am getting the echo.
We will resolve it in a short.
Okay. Shall I continue, ma'am?
Yes, sir. Now you can continue.
Okay, so we can specify which optimizer we need to use. See, different optimizer performs in a different way. They are meant for different purpose. We need to understand that one. So, and also metrics, like which metric should be used for evaluation, like either accuracy. If you are using any prediction, you can use a root mean square error or R2 score error or something, MSC, all those things we can mention. And this creates a model. And in case of machine learning, normally we go for cross validations. We can specify the k-fold cross validation, how many number of splits of the data has to be done, and how the cross validation has to be done, and result has to be generated. So if you see, you take any architecture, means any data set, this is a simple program, that's all. Only we need to change these three lines, means architecture. This is what changeable. Remaining things, just loading the data set and pre-processing the data set, it is left to you. So even when we go for multi-layer architectures or deep neural networks, so it's just whatever which I am sharing. It's a single layer architecture, means a single hidden layer architecture. So if you want like 4 5 architectures, just add model.add. That's all. Model.add a dense. This is for creating the neural network architectures. So once you run, this is what, like I said about the epochs. So in each epoch, whatever the data we had, 150 data has been passed to the network, and it has trained, and it will give the training loss and training accuracy. So at last, we will have the actual accuracy, and we will display. Similarly for images also. So this example is for MNIST, means digit classification, which has around 60,000 images, which is each image is of size 28 by 28. It is 0 to 9 English numeral classification. You can load it. So here also you can see the way of writing the program, means creating the architecture. It is just adding the dense, model.add dense, the number of pixels is equal to 32 by 32 input dimensions, and which activation function you need to use, and all those things. And remaining things remain same almost, only reading the data and architecture you have to change. So in the entire neural network, the implementation, if you use Cafe or TensorFlow or Theano or MNT or something else also, it will be same thing. Only you have to identify which function has to be used. So on training, just I have trained for 2 epochs. The error rate is about 2.90, means around 97% accuracy I have got it. I have already trained it to reduce the time. Okay. So this is a simple demo on multi-class classifications, this one. So just to note, the first question is how to initialize the weights. Normally, the weights are initialized randomly in a uniform interval. We will specify the uniform interval, or normally it will be specified by the platform. There are some other suggestions, like in 2010, Glort and Binjigo, they have suggested the weight should be in this range. If it is a shallow network, if it is a deep neural network, the weights should be in this way. Like this way, we can use some initializers. Okay, and the second one is the very important the dropout, which I was mentioning in the previous sections. So what is this dropout means? Like we will be having the connections between the two layers, right? Or in the entire neural network, it is made up of nodes and connections. So what I will do, I will take epoch 1. In epoch 1, I will try to mask some connections. Mask some connections means just make it as an hidden, so that a connection or edge will not participate in the training. So we will get the results, the weights will be updated. Okay, in the second epoch, we will retrain the older connections or edges, and we will mask some other edges. Like this way, if you do it, it will be very good. So what is the advantage of doing this one is it is very good for regularization. Means it will not try to overfit or underfit, and also it will try to do good yield a good performance on the unseen data. So dropout is very good, but this dropout works very fine when we have large network architectures. If you have a small architectures and if you try it, it may not be feasible. Normally, we try to use it on a large architectures, especially when we are using deep neural networks. So it will work. It's a very good approach. Another one is normally while training, what we will do, there are different ways of training the neural network. So either we can train the neural network, like if I take a POP1, I can feed one image at a time and then update the weights and then feed the second image. Okay, that is one type of training the neural network. Second one is full, like entire data set will be given. Okay, means one by one, the weights will not be updated until the entire data set passes through the network architecture, and based on that we will calculate the error and then we will try to update it. But both of them have limitations. Like if it is a first approach, it will be very slow and it may not be very good approximations of the weights. Same way, even if you do it everything, it may not be able to generalize it properly. So for that, we have a concept called as mini batches, where we will take a batch of data. Like let us say if I have 1,000 samples, I will send 100 samples in one batch, try to show 100 samples, okay, in one batch, and then update the weight and then show next 100 batches. So compared to first two earlier, so this mini batch works very good, and mostly it is to speed the process also. So normally, whenever we train any neural networks or deep neural networks, we use mini batches. So I recommend you to use mini batches. However, you can do experiment and understand what happens if you use single or full or mini batches. Okay, so this is what I planned for session one, just a basic understanding of the mini batches. Okay, now let us try to understand how this neural network can be used for video analytics. So the overall presentation is planned like this. First, I will give the basic structure of a video. Okay, how video is composed and what are the components of video, and there are different stages of video processing. So in each processing, how we can use neural network, I will take a simple case study, and at last I will take a case study of simple object detection, generated object detection using neural network. And I will try to give what is the limitations of this neural network on video analytics, why we can't use whatever we have learned in the first session for video analytics, what are those limitations, how this has been tackled, which is the appropriate area if you want to do video analytics, that will be discussed in this session. So we this is just a example, like videos and all those things. This is the older one. Applications, like normally videos, we have videos everywhere, right? So with respect to different categories, like we have different applications like news video, sports video, and so on. So in these applications, depending upon the type of the problem, we need to do some analytics on these videos. Example, let me take of a example of a surveillance video. So if it is a surveillance video, or if it is, if I want to identify an unknown person entering into my house, right? So how can I identify? Means video analytics in the real time. So in the camera itself, CCTV itself, we can have a chip with the algorithm which recognize the unauthorized person and notify to the owner or user. So such things, or identifying the objects in a video, like industrial objects or medical videos, identifying if it is for robotics, identifying the surgical equipments, and identifying and locating it. Or if it is educational videos, identifying the videos of my interest, like I want to find videos related to this one. So how these things can be identified, these things. So why we have so much of videos? Like videos are more effective compared to other data types, like audio or text, or non-structured or structured data. Because video gives more information than any other data types. Like reading, the user has to read and understand. Whereas if I take the video, so the video, even if I could not understand the audio of that one, by the acting or by what is going on in the video, the user can inference. So video is more effective than image or text. That's why, like, we have so much of videos. We collect videos. And another reason is affordable price of digital media. Like we are getting very good cameras, or even nowadays we have all mobile phones, right? Where we can capture the videos and collect a huge collection of videos. So we have too much of videos. But the main problem with this collection is, how can I organize and manage it? So that is one of the main problem that we are facing. So my research topic while doing my PhD was on a video database management system, video archival and retrieval system. So I have taken a simple example of that one for this session. So managing manually, it is a very time-consuming process. Like even if take our personal laptops, like, right, so our systems, we will be having huge collection of videos. What we will do, either we download or we collect it from friends or somewhere we bring, and we save it in our laptops. And whenever we require, it's like we have to search for the videos. If we have forget, like where we have kept our videos, so identifying that one is very challenging. So automating is a very good things. Okay, so how can we store it effectively? How can we retrieve the data very fastly and accurately is one of the challenges in video data base management system. So first, let us try to understand the structure of a video. Most of you know that video is a three-dimensional data, like image is a two-dimensional data, or any signal is a one-dimensional data. Video is a three-dimensional data where we will be having x and y coordinate, the spatial coordinates similar to image. Along with that, we will be having an additional dimension called as temporal t. So it's the same as like our image, but the image will be placed on a time. The changed image will be placed on a time. So video is a three-dimensional data. So normally, video is made up of multiple scenes. Okay, so each scene will give a particular information. Okay, and each scene is made up of several shots. So we can have several shots, and shots are made up of frames. So if I take a shot, let us say I have a shot of some 10 seconds, and I have a frame rate of 30 frames per second, I will be having 300 frames. Means in 1 second, we have captured around 30 frames. So there will be lot of duplications. Means same frame will be present multiple times. So when we see these frames continuously on a time domain, it forms a short scene and a video. So if you want to do any analysis on a video, especially for a database management system, we need to split the data into these lower levels. Like either we have to split into shots, or we need to split it into frames. When we split into frames, right, keeping all frames may not be efficient, because it's a redundant. So in that case, we need to identify important frames. We call it as a keyframes. So overall, for this video database management system, or for some video analytics, we need to identify the shots, okay, and or we need to identify the keyframes. So based on that, we can store effectively and represent the data in a more efficient manner. So let us see like how this video search engines means video database management means system means it's a search engine, right? So how this works? Normally we have three categories of search engines. One is text based. So this is what normally we use either in YouTube or in like a Google search or Alta Vista or something. We just enter the search whatever the video I want. Like if I want to see a video related to neural networks by Andrew Ng, right? I can give a search in the search bar. I can type neural networks by Andrew Ng. So that time I will get the system retrieves all the videos related to neural networks by Andrew Ng. The third category is oral based, which is not so famous like this one, where I can just give a voice command and search the videos. However, we can see that like Google's or something like Alexa we have, where we can say like we are getting the smart TVs nowadays, right? Where we can issue a command by voice, like where I can ask, okay, show me the videos. Like even in Google search, if I say Google, can you show me the videos of Tom and Jerry, so it will retrieve the videos of the Tom and Jerry, right? So we have both a text based and oral based. The third category is a visual based approach. Visual based approaches, it is neither a user giving a text as a query or a voice command as a query. Instead of that, you will give a video itself as a query to the system. Let us say that I am new to some game. Let us take a snooker game. I don't know what is the snooker game or how it works. So, but I love the event, like how they play and all those things. I don't know what the name of that game also. But what I have just a clip of that game. So I will take that clip and I will give it as a query to the system. Means video clip itself is a query to the system. Now the search engine or the system has to understand that video, okay, and then it has to search in its database and retrieve the videos similar to that one. That is one of the most challenging visual based. So under this we have like keyframe based or object based or semantic based. Keyframe means, so from the video, so what they will do, as I said, they will extract the important frames. Now the frames are nothing but the images. From the images, they will extract the features. Those features are represented in a database index stored. So for all the videos, whatever they have the collection, they will create a repository. Whenever a user use a query, that query video will be given, keyframes will be extracted, features will be extracted, and that will be matched with the database, and similar videos will be retrieved. So second category is object-based retrieval, where the system will identify the objects present in the videos and index it for all the data sets, whatever it has. And whenever a query is given, it identifies the objects present in the query video. Based on that, it will retrieve the videos. The semantic-based, it's a little bit complicated, where it will try to identify the objects, okay, identify the events, study the semantic relationship between the objects and the events, and based on that it will try to identify means retrieve the videos. So today we will see like how this keyframe and object based can be used using the neural networks. So first we will try to understand, this is the overall architecture of video archival and retrieval systems. Normally if you have a video, so you extract the frames, and from the frames you identify the shots. So we call it as a short boundary detections. Once shots are identified, from the shots you extract the keyframes, and for each keyframe you extract the representation and store it in the database. When the user comes for the retrieval and when the user uses a query, the query video, same process, like it will identify the shots, keyframes, and the video representations will be extracted, and that will be matched with the video database, and similar types of videos will be retrieved. So first we'll try to understand this short boundary detection and keyframe selection, and how neural network can be used to use this one. Nowadays, like as I said, this neural network now it has become the old technique. Means everyone is behind deep neural networks. However, my presentation will be based on the conventional neural networks. So what is this short boundary detection? Let us try to see the short boundary detection. So as I said, short boundary detection, it is a process of splitting the scenes into several shots. Means a scene is made up of several shots. So we need to identify those shots. So where they have combined two different shots, we need to identify and we need to make it separate. Because see, we could have processed the entire scene itself, but a scene will be a huge data. Like, or else somebody may say that I will be work on a computer complete a video itself. So video or scene will be very huge data, which will be difficult to process by the computers. So we work at either at the short levels or at the keyframes levels. So let us see. This is an example. Like what are the different types? Like this is what called as a shots. Like scenes are made up of several shots, right? So one shot and another shot they have combined. So this is called as a shot boundary. So the purpose of shot boundary detection is we need to identify this boundary. So now we will get the frames. So from the frames, we will extract the feature representation, and then we will try to compare the representation from one frame to another frame. If there is a too much of change in the distribution of the feature or change in the feature structure, then we will try to identify the boundary. Okay, so it's in this diagram I have mentioned like it's a very straightforward, but there is a challenging involved because we have different types of transitions. Short transitions can be abrupt or cut or gradual transition. Cut means as I shown, there is a sudden change from one frame to another frame. There is a sudden change, and that is a short. So identifying this transition, the cut transition is very simple, and they have achieved more than 99% accuracy. The another one is gradual transitions, where from one shot to another shots, the frames are mixed very slowly using some graphical things. Like they use graphics to merge two shots, like dissolve, wipe, fade in, or fade out. I will show you a simple of this one. So if you see here, the dissolve. The previous shot and the next shot frame has been merged together. So if you try to estimate the difference may not be much, too much, so that it may be difficult. Or gradual transitions. So transitions, it will be in this case. If I try to use a simple representation at the rate of change, right? Every frame becomes a shots. Then it's a waste. Like this is what very challenging, right? Whether it is a gradual fade in, fade out, right? Identifying the short boundary is very difficult. So short boundary detection. So what we need to do in case of short boundary detection is it's a process of splitting a scene into basic video shots. Okay, so we will be having continuous frames. So continuous frames will be coming. We need to do the analysis and we need to identify which is the boundary, and we need to split entire set of frames as a short one and a short two. So that is what short boundary detection. So this is an example of cut by if it is gradual transitions, it will be very difficult. Now let us see like how this one can be identified. As we observed that the frames surrounding to a boundary generally have a significant change. So we will be having a significant change in their visual content. So we need to identify the visual content, analyze that one, and see that whether there is a high rate of change in the visual content or not. If yes, then we can say it's a short boundary. In case of gradual detection, short boundary detection, it's not like we can't do for one single frame. We can't just take two frames and do what is the rate of change. In that case, what we will do, we take a set of frames. Let us say I will be having a window. If I am at a frame number high, so I will, let us say I will create a window of size n. So I will take n frames. behind the ith frame, means I minus n frames will be taken, as well as we will take the next n frames, means totally we will take 2n frames plus 1, including the frame which we are interested to say whether it is a boundary or not, and we do some analysis, and based on that we will take a decision. Okay, this is a boundary or not, whether it is a gradual transition or not. This is done for gradual transitions. So I will take a use case of a neural network based scene change detection for video classification, which was proposed in 1993. As I said, that because we are using neural network, I am using the old research articles, this one. So this paper was by Mallikarjun Rao, Ramakrishnan, and Balakrishnan from IISc, and Srinivasan from another robotics laboratory. So they have identified this one. So what they have done in this article, like I will just open the article also. Okay. So in this article, they have taken a video and they have extracted the frames, and their main aim is to identify the gradual transitions like fade in, fade out, dissolve, or a while. Okay, because identifying the cut is not a challenging issue. Normally everyone takes in gradual transitions. Okay, so how this architecture is implemented is, it's a very simple, straightforward architecture. So see, as I said, the neural network architecture needs some input features. Now we need to extract the features from the frames. So for that, they have chosen following features, right? Like number of intra-coded blocks, number of threshold exceeded intra-coded blocks. So totally like 6 features: frame type, and whether it is a p type, and number of macro blocks. These things are the features which we get from the MPEG. If it is a MPEG encoding, if you decode it, we will get these details. So these details for each frame they have extracted, and that has been used for identifying the short boundaries. So now you can see that for each frame what we have 6 features. So we can have these 6 features. We can create a neural network architecture like whatever we have shown. So this neural network architecture can be fed, means to that neural network architecture, this feature can be fed to identify whether it is a gradual transitions or not. If gradual transition, what type of gradual transition? So what they have done, as I said, for gradual transitions, we need to take multiple frames. So it cannot be processed by a single frame. So in this work also, what they have taken a single frame, like the frame which need to be taken care as whether it is a short boundary or not. They will take previous n frames and next n frames, and for all those n frames they will extract the 6 features, and we have to create a ground truth for that one, whether it is a gradual transitions or not. Means we should have a label for that one. So they will create a label, it is a wipe or a short dissolve or a fade in or a fade out, and that was fed to the neural network. It's a simple architecture. They have not given the complete architecture details. Okay, so assuming that probably it may be 1 or 2 hidden layer architectures. So assuming that we will be having 6 input, so totally the number of features will be 2n plus 1 into 6 feature representation. It's not a 6, so it is 2n plus 1 into 6, because we are considering 2n plus 1 into 6 frames for analysis. So the number of inputs in that architecture will be equal to 2n plus 1 into 6. And number of outputs is, they have taken 4 different cases: fade in, fade out, dissolve, and wipe. So 4 output nodes will be there, and they are not given complete architecture of their architecture. Assuming that it's a 2 hidden layer architectures, they will feed this one, and they will train over the data set whatever they have collected, and based on that, they are able to identify whether it is a scene change or not. Means here scene change means it's whether it is a short boundary or not. This is one of the work published by these authors, and it's a very simple to implement also. If anybody working on video classification or something, if they want to try out rather than going to a deep neural network, this can be implemented very. So like this way, in general, if you want to do any scene change detection or short boundary detection, what we can do is collect set of frames. Okay, from that frames you can extract any features. Like these people have used MPEG coded features, right? Instead of that, you can think about using the color features, texture features, or shape features. Like anything for each frame, you extract it and preserve it. But the main problem with this approach is the identifying the boundary, means generating the labels. See, another issue with this short boundary detection is, if I want to do a short boundary detection, first I should create a data set. For each frame, I should have a label whether it is a short boundary or not. So that will take too much of time. However, we have a certain standard publicly available data set, like a TrackBit data set. So you can use those data set to do this process, which they give the ground truth where the short boundaries are there and all those things. Okay, the next one is keyframe selection approach. Like another way of this one video analytics, we can extract the keyframes instead of working on the shot. Like if we have a videos, right? So video is made up of several frames with the repetitive frames. In that case, what we need to do is we need to identify a frame which represent a set of frames. Example, a shot may have some 1,000 frames, right? In one shot, there may be a gradual change. Example, whatever the frames I have shown here, it's made up of a single shot. Okay, so here we can extract a frame which represent a set of frames. So normally we use a time sampling method or frame proximity method. Time sampling method means for each interval of a time we select frames and we will try to extract the frames as a keyframes. Frame proximity means we will try to study the relationship between the means extract the features, study how they are same or not. For a set of frames, if the it is changing, then we can identify as a keyframes. So one of the authors, like these authors, they have presented a neural network approach to extract keyframes. So they have used a combination of two things. One is fuzzy as well as spatial distribution of the activity. So, and based on that, they will try to identify, they will feed those features to the neural network and they will identify whether it is a keyframe or not. See, for this, the input is a short segmentation, means the short boundary has to be extracted. Now, for the short, for all the frames in the short, they will extract the features. Means they have extracted the motion features. So motion features they have extracted and they have taken two directions. One is to study with respect to the fuzzy to identify whether it can be a keyframe or not. Okay, and the spatial distribution. See, this spatial distribution means whenever we have a motion, right? So probably entire frame means all the pixels in that frame may not have a motion. Okay, if it is a particular object. Okay, or there may be another case where there is a high rate of change in the spatial distributions whenever, like when camera is moving along with the scene. See, in case of, there are two cases we have to understand for this spatial distribution. When camera is static and scene is changing. Second one is when both scene as well as camera is changing. So spatial distribution will be very less when camera is static, only the scene is being changed. Whereas in case of camera is moving, as well as the scene is changing, there will be a lot of spatial distribution. So these things has been extracted in a form of features, and these features has been fed to the neural network. So we can extract now for this for each frame we will be having the information, and based on that we can identify whether the current frame can be selected as a key frame or not. Here also, in case of a keyframe, it's not like based on a single frame. We can't take a decision like this frame can be a keyframe. Even in that case, we need to study a set of frames which are in the vicinity of the current frame. So that also very important. See, even in case of short boundary and in case of keyframes extraction, this is the problem that we are facing. Why I am taking this one? Because this is one of the limitations of the classical machine learning or this neural network, especially for video analytics. See, in case of image or structured data like iris data or wine data set, right? There is no temporal information. We are not bothered about the temporal information. When it comes to video analytics, temporal and spatial matters. So these machine learning algorithms, it may be neural network or support vector machines or anything, they are not able to capture the spatial and temporal relationships. That is one of the major limitations. So they are not able to capture the spatial relationships also, that I will explain you in detail later. So in this paper, they have taken several features. Means two features. One is motion intensity based on the membership functions and spatial distribution localization, and that has been fed to the neural network to identify the keyframe. So this is another example of keyframe extraction using a neural network approach. So coming to the last part of this one, like object detection using the neural networks. So now from these two, what we understood, right? The neural network is not capable of taking care of spatial as well as temporal features. So how can I do the object detection in videos? That is another challenging question. So if you see, a video is made up of frames. Frames are nothing but internally an image, right? So what we can do is, so we can detect the objects in frame as detecting object in images, and we can use some simple tricks like what is the change, how much pixels has been changed or not, to identify what is the probable candidate in the next frame for the object detection. Okay, and based on that, in the next frame we get a guess. Okay, probably the in the previous frame the object was at this location, like x comma y with w and h with so much of width and height, and then in the next frame we can predict a intelligent guess can be done, and based on that guess we can identify whether that object is present or not. So like that way, there are multiple methods to do that one. So normally for object detection using neural networks, what we will do, we do it as a object detection in frames. So we extract the frame, and treating it as an image, we identify the object, and then in the next frame we will try to see whether the same object is present or not. If not, we will try to see if there are any other objects. So as I could not get much of the works on object detections using neural networks, so but if you search in Google like object detection in neural networks, you will get only based on deep neural networks like convolution neural networks like YOLO architecture, RCNN, and MRCNN, and so on, which will be discussed in tomorrow's session. However, I could find one blog where one of the author has used a neural network, a simple neural network for object detection. So that I have taken as a case study here. Directly, I have taken code from that repository, and I'm just showing you. So how this code will work is the neural network. They have used a simple feed-forward neural network, and they assume that each frame or each image is of size 8 by 8. Inside that 8 by 8, they will try to put the objects. So for sake of simplicity, first I have taken simple program like rectangles. Some bounding boxes are there, assuming that bounding boxes are rectangles. So it is just like a white background with black rectangles or bounding boxes, and those boxes will be treated as a object. So I have taken two simple examples. One is a single object, another one is a two object. Now let us try to see how this object detection, a single object detection works. See, working principle is very simple. See, what these neural networks will do, it will take inputs and it predicts the outputs, correct? So what we can do is, you take a frame, okay? For each frame, you identify what is the location of the object. So as of now, we will consider a simple example like a frame contains only one object, a single object. For that object, we will be having the information about the x and y coordinate. X and y coordinate means normally we use top, bottom, left coordinate, like left and right 0, comma 0. So we will have the coordinate in that frame like 8 by 8. Along with that, we will be having what is the width of the object and what is the height of the object. Okay, so for each frame, given a frame f1, we will be having these four information: x, y, width, and height. So now we will do the same thing for all the frames, and that will be fed. The frame as well as the y will be these parameters. See, in the previous cases, whatever we saw in classification problem, right? So in the classification problem, we had only one variable called as y. Like if I take the iris data set, it's a class label, whether it is iris setosa, virginica, or versicolor, means 0, 1, or 2. So it's a single character, a single digit, right? Whereas in this case, given a frame, I will be having four more parameters: x, y, w, and h. So this is what need to be predicted by the neural network. So neural network has to take frame as an input. Frame means a 8 by 8 matrix. If we vectorize that one, it will be a 64 values that will be given as an input, and the output what we expect is x, y, w, and h. For each frame, it has to predict it. So we will not worry about the architecture. So we will just understand for time being how this will work. So now in our data set, what we will do, we will try to create the frames by program. In this program, it has been created programmatically. So a frame is created, means an image is created. Randomly, an object has been placed, and for each frame, the location of that object in each frame, the coordinate values, width, and height has been stored in a text file and or in a NumPy array, and that has been fed to the neural network. Now the neural network, it's a single, just I have used a simple single dense layer, okay, which predicts these four values. And as this is a prediction, we are not using accuracy as a measure. We are using the mean squared error as a measure to update the loss values. Like for back propagation. Initially, it generates x, y, w, and h. So it will compare with the actual x, y, and w, h. So there will be error, and that will be feedback to the algorithm. It will try to update its weight, and then it will try to generate the new set of values. Okay. Now let us see how this program works. So here nothing has been used, like a simple numpy has been used. So these are the packages that I have imported. Matplotlib for plotting the images and displaying, numpy for this neural network and the implementation. Okay. The next one is create images with the random rectangles and bounding boxes. So image size is 8 by 8. Okay. So minimum object size is 1 pixel and maximum object size is 4 pixel. So number of objects should be equal to 1. So this snippet code cell will generate a set of images. So it generates around 50,000 images. Okay. So like this. So this is a frame for me now, and there is a object. My problem is, if I input this as an image, right, I should get a rectangle box to need to be fitted to this one. Okay. So normally for this we need to reshape the data into standard format and all those things. So y will be our rectangle boxes that has been generated. Here you can see that we are generating a random value with this one, w and h, x and y, and image has been generated, and boxes has been stored. Means the x, y, w, h has been stored in b boxes variable. Means it's a numpy array. So this has been used as a y, means which need to be predicted. This also been normalized. So the data set has been split into train and test data set and building the model. Here also you can see that it's a very simple model that has been used. See, that's why I said. So just we need to understand how we need to give the data to our model. That's all. And creating this model is not a critical issue. So we can give like dense as a 200. Okay. So it's just like input layer, one hidden layer, and output layer. Okay. So this will give me a out, and we have at last a dense y dot shape of -1, means it will be equal to the number of parameters in y, which is equal to 4. Okay. So this will be trained. Now we need to fit this model. So we will try to fit the model. We can specify how many number of epochs, validation data, and all those things. And based on that, we can predict the bounding boxes on the test images. So here we have the test images. Normally, how we will compare this one is, see, I will be having the test image. So I will XYWH will be predicted by the neural network. Now I need to compare how good it is mine. For that we have a measure called as IOU measure, intersection of union. Intersection of union means it will take the X, Y, W, H predicted from the neural network and the expected output, that is x, y, w, h, and it will try to see how these bounding boxes are intersect, how to what level these bounding boxes are intersected. So it normally ranges from 0 to 1. 1 means it is a total intersection, 0 means no intersection. So if it is 1, we can say that our prediction is very good. 0 means very bad. 0.5 means it is a 50%. So based on that, we can generate the IOU. This function generates a IOU and return the IOU. Okay. So here is a simple example which taken and predicted the values. So in this diagram, you can see that if I take the actual output, which is black, and the red box, which is predicted by the algorithm, in the first image, the first, second, and third image, it is 0 IOU. Whereas for the fourth image, it has some IOU which is not visible. Okay. So like this way, we can calculate the IOU. Means in case of object detection, the output will be like this, given a frame and given an object. So what we have to do is we have to just, I will try to run it like I have run only for some 30 epochs. Probably you have to run it for some 400, 500 or 1000 epochs. You may get very good results. Okay. In case of object detection, what we will do, given a frame, we will try to fix up the bounding box. So that is called as object detection. So this is an example of a single object detection. Right. Same way, if I want to do it for multiple object, like I've opened the second program for two rectangles, means two boxes. If we have two boxes, how we can check that one? The idea is same. The only the change will be here is, see, given a frame in the previous case where we had a single object, right? So the output, the expected output was 4 values. Now here it becomes 8 values, because we are trying to find the number of objects is equal to 2. So for each object we need to find out the coordinates and the width and height. So because of that we will be having the 8 values. So we need to generate the data in such a way that we will be having this one. So that has to be same way, just generate the data and feed to the neural network. So some tricks has to be used here, just to make it like when we have same image flipped or not or something, we will use that one, and we will train the model and we will try to generate the results. Okay, so if we analyze this one, right? So this is what the mean MSC during the training and all those things. So here you can see the output. So this was trained for more number of epochs. So you can see that we have much overlapping. So there were some misclassifications and all those things. So yeah, same here also IOU has been used as a measure to map the results, the targeted the actual output and the generated output. So implementation wise, if you want to do it on a neural network, you can implement using this one. The same author has been used for detecting multiple objects. This has been exploited in deep neural networks. So here, which can use to identify multiple objects. So we saw about identifying the objects. It's we say that it's a localization of the object. Localization means where does the object locate in the frame. That's all. The still the challenging issue in this one is, along with the object localization, we need to also understand on object classification, like which object it is. So which object it is? So here it is a rectangle. Like let us take some industrial object recognition. Like we may have several industrial objects like spanner, screwdriver, and so on. Right. So if we locate, it's not only required to locate where it is. We need to label which object it is. So it's a once again classification problem. Even in that case, you can use a neural network for object classifications. So in the literature, you can find multiple articles where they have used neural network for object classification, but for detection, it's very few. However, with the advent of new this one deep neural networks, object detection, localization, and classification, it has been achieved to greater extent. The next problem with the video analytics is about semantic analysis of the video, understanding the meaning of the video. So for that, these things are required, like short boundary detection or keyframe selection or object detection, object classification, then studying the spatial and temporal relationship, identifying the events in the videos, those things. So for this, you can use neural networks. So now this is what the simple thing that I planned for video analytics. This one. Now let us try to see the limitations of the networks. So limitations. One of the major limitations of the neural network is, like someone asked in the questions, like what should be the depth of the neural network, right? So here is an example. Like if you have linearly separable data, then architecture without any hidden layers, it can be resolved. So if it is a non-linear separable data, then better you think about layer or layer. So when it comes to non-linearly separable data, you need to think like understanding of the data is very important. See, for machine learning, prior to identifying the machine learning algorithm to be used for classification or clustering or regression or other purpose, first we need to identify or understand the data. Example, in this image, we can see that in the second row, it has a convex example where we have the A and B, the same data which we created for understanding the this one. Uh, Functions, right? So if you have a proper understanding of the data and proper understanding of machine learning technique, it will be very easy. Just a trial and error approach where we have to do trial and error approach and we have to identify. Example, if I know, like if I take the data, if I know that it's open and data distribution is like this, or a structure of the data in the feature space is like this, I can directly say that okay, you use a architecture. Normally questions will be arises, okay, which architecture is best for my data or my problem. So it cannot be answered. We have to see data, we have to understand the data, then only we can recommend, okay, your data looks like this, it is having this property, so for this type of layer architecture is better, you go ahead with this layer architecture, that we can do. Or simply without seeing the data or understanding, just may or may not work, or 99% like it not work. Once you understand the data and once you have complete understanding of your machine, then it will be good to see. Another major limitation is the number of hidden layers. See, and activations functions what we are using. So we are in a confusion when we go for neural networks, right? So how many hidden layers need to be used, or which activation function has to be used? If the input size is less, if the input size is large, what happens? See, and the input size is large and the data is very complex, right? If you try to design a huge network architecture, it becomes extremely large. When it becomes a large network, right, the number of parameters need to be identified the neural network will be more. uh, Example, if you take this one, this is an image of 16 by 16, means 256 inputs will be there. So if you take the first input layer and the first input layer and the first hidden layer, so in the hidden layer there are 100 units, right? So each unit in the input each node in the input layer is connected to 100, means 100 into 256, so totally 25,600 connections will be there. Means what, we need to identify 25,600 parameters just to connect input layer to the hidden layer, correct? And in the hidden layer we have 100, right? So we have 100, right? So for that there will be one bias parameter. So one means for each node, one means there will be totally 100, so 100 parameters. Next, so we have here 100, so from there it's a, digit English character recognition. So 26, so in the output layer we will be having 26 nodes. Now 100 into 26, so 2600 plus 26 bias. So totally, if you see for this architecture, it is about 28,320 parameters has to be learned by the neural network. So this is more complex. However, neural network will do, but it will take time. See, one of the major limitations of the neural network is the training. See, mainly people say that training is an offline, but times it will be very challenging even when the training time exceeds. Example, I will just give you an example of our work. So we are working on defect detections or in the MLCC chips. MLCC, it is very small. It is smaller than our particle as particle. Okay, so in that we need to identify when it is manufactured. We need to identify the this one. whether it has a defect or not. If it is a defect, whether it can be repaired or not. Sometimes such things. So if I use a neural network, right? So normally, if I have we will be having millions of images. So if I want to train, so if I put it for a training, it will take around, let us say, with a higher end system, it will train for some 5 to 6 hours to get the output. So once I get the output, I will come to a conclusion. Okay, this architecture is having issue or data is having issue. Then I have to change it. Okay, if I change some architecture or data or something, for next output I have to wait for another 6 or 7 hours. So to finalize that itself, it will take too much of time. If I take image classification, some of our algorithms, it will run for one, it will take around 2 to 3 days for training, just to see the output. Once, even with like a volta 100 gpus. Okay, so even with that, it will take a huge amount of all those things, because we have some images where each image is of size of 20 GB. One image size will be of, means that much of high resolution images captured for PCB boards or some other instruments and all those things. So that will take 2 to 3 days. So I will wait for 2 to 3 days. After that, I will come to know, okay, whatever I trained for 2 to 3 days had this limitation. Then change again. See, this is one of the major limitations of the neural networks. But the advantage of the neural network is, once you finalize that one, the inference, that testing time is very faster than any others, because it's a very simple operations. It is faster than any other techniques. So in case of neural networks, when the architecture becomes large, the parameters will be very huge. So this will take too much of time. That is one of the limitations. Another one, this neural networks for image or video analytics, they are very good in some distortions and all those things. Means, if your data is not proper, means what I am trying to say here is, if your training data, if your training data doesn't have a good population of input, right, your neural network will not work. Example, let us say I have a standard data set without any distortions or anything, like geometrical transformation, like shifting, scaling and other things. So there will be change in the input itself, right? So in that case, definitely neural network will not able to give very good response when it is deployed. So it depends on the data, but if you have data included, such a data in your training set, right, definitely it can do wonders. But if your data is not good, then it will be an issue. That's why, compared to all other machine learning algorithms, this neural network and Bayesian classification requires a huge amount of data for training, and collecting a huge amount of data is another challenging issue. So I will just quote an example. Like we will work on defect detection in PCBs or some other chips in our company. See, getting a so there are two classes. Let us take two classes. One is a non-defect. Another one is a defect class. Getting a data for a non-defect is very easy, but getting a data for a defect class, which includes all variations, it's very difficult, because we don't know. Like, it depends on machines, it depends on the engineers, how they manufacture, means how they feed the data or parameters or raw materials and all those things. So if we won't get the data for things, means if the distribution of the data among the classes is not good, then this neural network will not work. So we have to maintain that distribution, and getting that one is very difficult. Another problem with this neural network, as I said just 5 minutes back, like these neural networks are not capable of preserving the spatial and temporal information. Like we saw, right? Like we took a image 16 by 16 and we vectorized it. When I vectorized it, there is no spatial information about the important pixels, right? So it is just vectorized. I lost the actual information. right? Or if I take video analytics case, right, the temporal is very important for me. So how I feed this temporal information? See, people like Ramakrishnan or some other what we discussed for short boundary and keyframe. So they have taken 6 or 10 frames in the vicinity of a given frame, and they have concatenated. But that will not give you a temporal information at all. So these are one of the major issues in the neural networks. So they work on the raw data, but they lost the topological information, spatial informations, and temporal informations, which is very essential for today's applications. So overall, if I want to conclude my sessions, 2 sessions summarize, right? So in this neural network, the main thing is the neural networks are very good in similar to our human brain, right? Unlike other machine learning algorithms, these neural networks required a feature extraction, like we saw, right? So if you want to do any learning algorithms, we need feature extraction. See, for that, feature engineering has to be done. One person has to be dedicated for feature engineering. He should have a domain knowledge of that one. So that is one of the limitations of all machine learning algorithms, even neural networks. So it requires feature extraction prior to learning. That is one of the major limitations of all machine learning, classical machine learning algorithms like SVM, Bayesian classification, neural networks, or you take anything. Okay, and neural networks do not work well for preserving spatial and temporal informations. Okay, and as increases the data increases, the architecture complexity increases, the number of parameters also increases, and it makes complex. Training timing is more, but inference time is very less. So how can we means making deeper networks initially was very difficult. Nowadays we are thinking about the deeper networks. So solution for all these things means where the user should not bother about feature extraction. See, for many of you, if you're working on computer vision related applications, normally we used to scratch our head for identifying the features, like which feature I need to extract for my application, right? Once I get the complete domain knowledge, then only I will be able to understand, okay, for this shape features are very good, for this color features are very good. So for that I need to spend too much of time. So can we come out with a mechanism where this feature extraction can be done automatically by the system? I will not bother about the data. Just I will feed the data to the system. The system should be able to identify a suitable feature for learning. The next part in limitation is which learning algorithm should be used. This is a general question. Normally we are worried whether I should go for SVM or neural network or Bayesian classifier or something else, because there are 100 of learning algorithms which need to be used. That I am also like. So normally what we will do, if we don't have a proper knowledge about pattern recognition or machine learning, we do trial and error approach. We do all possible ways of testing, and then we say, okay, this approach is the better. So instead of that, can the system by itself, can we use any architecture or any learning algorithm so that it will identify the features by itself and learn, and it produces the output? That is achieved in deep neural networks called as deep learning, where deep learning we use this one. The limitations of neural networks has been overcome. So in tomorrow's session, Dinesh sir, he will explain in detail, like, okay, with the limitations of neural network, how we can design a system, a neural network based system, which combines feature extraction and learning together, reducing the burden of the user. So automatically it will identify the features, and using the simple neural network, like whatever we have learned, the dense neural network, right? Simple neural network architectures, we can solve any of the video analytics problem. Either it may be object detections or identifying video classifications, or anything that can be used. That will be explained in detail in tomorrow's session by Dinesh sir. So this is what I planned. These are the references. Many of the things I have taken from the web, and code I have taken. I have modified the code little bit so that I can run it on the data sets and these things. So this is what I planned for today's session.